welcome back. We're here again. So where we ended up was, yeah, we calculated the normal and we have the position. And now the nice thing is happening is we need to do some lighting that it looks more realistic. And I want to show a little bit of theory first. I made a little component to describe a little bit the different light effects. One part of it is, well, two parts. You have diffuse and specular light. Diffuse light is more a light ray hits a kind of surface. Okay, imagine like this white light is a surface of some ground, some floor. The yellow dot here is light, and this line is a light ray. When it hits an object, it's getting scattered away depending on the normal, so the angle, what we just calculated, perpendicular to the surface. It depends on how big the angle is with the ray shooting from the sun. In this case, it's the same. And so then you get the most diffuse light, the most light being diffused away from that position. But if the surface is like almost perpendicular to the ray, you get less lighting. So the blue lines here describe like how much light you get when a light ray hits the surface. Now, if you would plot this, you see it here. So I just colored here the amount of diffuse light blue. And as you can see here it's almost gone, so that's why it's black. So this type of light only depends on the normal position of the object and the light position. I mean, if you move the light, you see like the shading differ as well, because then yeah, you get different angles and that kind of stuff. Now the other one is specular lights, and specular lights comes down to that the light ray reflects on the surface. Also depends on the normal. I mean, if the normal points a different direction, it reflects in a different way. But it also depends on if that ray eventually hits your eye or not. If it hits your eye, you get more light, because then it kind of works like a mirror. You're seeing through the material, the reflection of the light, and you see the sun again. Now, if you plot this out, you get it like that. So in some situation, it gets close to your eye, so it gets more bright, but some situation it doesn't. And now it doesn't hit it anymore. Now, if you move the eye position, the specular highlight is moving and not the diffuse, because the diffuse doesn't depend on the eye, on the camera, but the specular highlight does, because it needs to reflect in your eye or not. Now, this is the very basic way of rendering light. There are more advanced way like PBR, and that takes in consideration that the surface is not that smooth, and that it can be rough, and that the ray is not reflecting perfectly and that kind of stuff. But for this case, we're just using the simpler light. Definitely because of water, we don't need much roughness. Water isn't rough. So in that sense, simple diffuse and specular highlights is enough. Yeah, we can play around with the surface a little bit, see what is happening. If you drag your mouse, then you move the line. So yeah, let's do it. This is the reason why we calculate the normal, because yeah, we need the normal for the diffuse, but also for the specular. So let's implement this. That's my code. Let's remove this board. So this is our scene right now. Very simple. We can do this movement here, because we have it anyways. like a nice smooth transition there. Okay. So we have the position and the normal. And now we need a color. So let's make a function called render. That we need the ray itself because we want to know which direction the ray is. In this case, the other way around. It's not the light ray, but the camera ray, the ray we are looking at. So we need it for the specular highlight. We need the position and we need the normal. And this should give us a color. So let's write this function. Let's return a RGB because we don't care about alpha right now. Render ray factory pay. I like to call it just P and N. I got so used to it, but I can imagine it's not very readable. So let's call it now position and normal. First, diffuse. So what we saw, it depends only on the light direction. So we need some light position. Where is the light? We're going to use a point light, very simple, like, okay, there's a point in space. From there on, all the light rays emitted all directions. So let's make a uniform for that. Light position. -3, 3, 1. Uniform. Okay. Now the light direction depends on the position where we are, and it's simply light direction would be light position minus the position. So now we get a line. So here, now we get this gray line. Yeah. This is the light position. This is position. So this minus that gets us this line. The length is this one, and the direction is also this. When you're talking about direction, it's always nice to normalize it again, especially doing linear algebra, calculating angles between directions. With normalized vectors, you can easily do this, but needs a little bit of linear algebra. Anyway, what we do need to know now is the angle between the normal. If the angle between the normal and this direction is 0, in other ways, it's the same direction, we get the most diffuse light. But if it's 1 in radians, or like now in radians, it's like, what is it? Quarter pi, like 90 degrees rotation, and we get no diffuse. And between it smooths it out. You can do this with linear algebra with a dot product. If you have the light direction and the normal, the dot product between a normalized vector length 1 and the normal, it's also length 1, gives us the cosine. This is the cosine of the angle between them. And since the cosine goes from -1 to 1, when they are, dot product, when they are the same, it becomes 1. Yeah, sorry. So what I just said was the other way around. So when they are the same, the angle, the dot product becomes 1. The cosine becomes 0. And because the cosine is 0, the dot product, the value of cosine is 1. So we don't want to have negative values, so we're maxing it out to 0. So only positive values. And this is already, it is the cosine. It's the cosine between the angle. And that's already perfect for diffuse lighting. If we return this, so it's just gray colors, the amount of diffuse we return as a color. We get a big error because syntax error at far because we forget a semicolon. Now, this is the diffuse lighting already. So similar to what we did with like plotting only the normal Y when the light was completely on top. That is the same thing, but now we can move the light around. And you already get a nice diffuse shading feeling. And as you can see, it doesn't matter where you move. Of course, you see it different because you look at it from a different position. But the light itself is not changing. It's not reflecting differently in the direction you look at it because it's diffuse. We're only taking care of the light direction and the normal. Okay. Now for specular highlights. Specular. Specular highlights. Let's look at this again. Yeah, we need to reflect the ray. So we have a light direction, but we need to reflect it with the surface based on the normal into the space again and see if the angle between our light direction is the same. And how we do this is super nice with GLSL because we don't need to do any math because there is a function called reflect, and it gets like two factors. The light direction reflecting with the normal. Now light direction, right now we have a factor from this position towards the light, but with the reflect, we want to reflect from the light to the position and then reflect it. So it should be minus the light direction. This gives now this factor going that way. It reflects on the normal. And now we have to check if it hits the eye. Now we can do the same with the dot product, but with specular highlighting, it's nice to, now first let's do the dot product. If this one is reflected arrow, reflected vector, is at the same direction of the view vector, but the other way around. View, the ray direction is from the eye to the surface, and this reflected is from the surface to the eye. So dot ray direction, the negative one, because we want to have from the position to the eye. See if that's the same direction. But now what looks good is not so much the whole, like this gives already a value. If it's almost like here, it already gives quite a big value. And what we want is only giving values when it's really close to the eye. And we can do this simply by taking the power of this value. Okay, make sure it's definitely 0 or bigger. And then we can take the power with a value. Let's call it shininess. It's 100 for now. And let's show how this looks. We get another error. 5. Again, semicolon. Okay. Now this looks beautiful. It's because of our huge shininess. If we take one, for example, yeah, here you can see if we move the camera, the reflection also changes a little bit. It's now darker here than when we look at here. So here you see the specular highlight. Now the specular highlight here is way too much. That's why I increased it, the shininess with a lot. And now we can add diffuse as well. And then you get highlights here. It's a little bit too much. Like you see it already that it's completely white here. It's exceeding 1. And that doesn't look good because then everything gets clamped. We cannot see like light above 1, value 1. So that's because diffuse gives like a value between 0 and 1, and the power specular as well. So this together should be, I guess, maximum 1. What we can do is like multiply it by a certain percentage, 70% of diffuse lighting, and now let's say 3% of specular height. Look, and then you get like a more nicely looking specular highlight. Yeah, that's about it for diffuse and specular highlights. So again, you can do more funky stuff with roughness and stuff with PBR materials. I did include it in the floating faucet, but again, I'm not sure it's working on a Mac. Sorry about that. And plus the shader functions I didn't write myself, but it's from TouchDesigner itself. I exported it, the same ones that's being used in the PBR material. But I exported it using my Windows PC, so that's why I guess it doesn't work on the Mac. Didn't investigate yet. Okay, so but yeah, we don't need PBR for now. We're just gonna do diffuse and specular highlights. But now the next step is refraction. We have the light now. We did this. Yeah, now it's time to like, okay, water is not like this solid stuff. It's not like that we see the surface and that's it. We want to look through it. We want to go through it, but it's also not like just through it. The direction of the ray is being changed. Like if you touch it, it's suddenly going to bend a little bit. And the reason why this is happening is because the speed of light in water is slower than in air. And when it's getting slower, it starts to bend. Not entirely sure how this is happening. Some people describe it like it gets slower, like a truck driving on a high-speed road, and then suddenly you get to some grass field with one wheel, and that one goes slower, so the car turns around. It makes a little bit sense, but I doubt it's happening like that. It doesn't. Well, anyways, that's physics. So yeah, we have this position now where we're at, but we want to continue raymarching. We want to know what's behind the water. So instead of what we did now in the code, is we march here one time, ending up at an object. We need to continue marching. We need to see like, okay, is this ending at the background, or are we still being able to go through the material? And how we do this is making a loop, which makes it even more expensive. So the whole raymarching technique, it is quite heavy. That's why you need quite a proper GPU. And especially if you have a high resolutions, then there are a lot of calculations being done. So you have to watch out a little bit for that. But there are some optimization functions as well, like that you only process like a distance field that's close to the area you are, and not like in detail asking the distance to any object in the space, even though it's behind you and stuff. But that gets more complicated. And we don't need it now because it's just 2 objects and it's quite fast. So let's make a loop. The times amount of bounces So also amounts, bounces, make a define for that. Not too many. Let's do like this 4. Top. Sorry if I go too quickly. But again, if you don't follow it, all those stuff, everything I'm doing is also in the docs file, in the .to file. So if you want to read the code more in depth, you can check that out. So in this loop, we need to raymarch. Okay, let's have a max distance. 10, for example, in the beginning, a little bit bigger, 50. And this color should be defined before the loop, because we only have one color. And then we need to add, for every bounce, we're going to add something to the color. If the distance to the object is bigger than the max distance or equal, that means we hit the background, and then we break, we jump out of the loop. Maybe we can add some background color here, but for now, let's keep it black. And then, if not, we're going to find the position of this distance, calculating the normal, rendering it. And instead of assigning it, we're going to add it. And let's forget about alpha for now. It's quite annoying. Let's do it like that and set this to default alpha is 1. Yeah. So what we did now is we doing the same raymarch 4 times in a row. So that doesn't make sense because after the bounce, we need to move the ray because the ray is still the camera ray, but the origin has changed. So the ray origin will be the new P, the P where we are at the moment. And now the tricky part, it's also quite easy to implement in GLSL, is refraction. And going back to this one to show a little bit what happens if you have a light ray like this, and this surface wouldn't be like a solid thing like the diffuse light what we did, but more like water. The ray would continue until it hits the bottom here. But with refraction, like I said, it's getting slower in water, so it changes direction a little bit. And I described it here, like that. So when it hits the surface, depending on the normal, it's being diverted a little bit, change of direction, then continue through the medium until it hits again something. Then in this case, specular highlight, it's being reflected again, being refracted again, changing direction, and eventually going to the surface. And either it can hit your eye or not. What I'm showing here now is caustics. Is what happens when you shine light on a water surface. You see like nice highlights on the bottom of the ocean, of the water. And that's because of the specular highlights being refracted through the water on the floor. The problem is now only is that we want to do everything in real time, and it's quite an issue to know which of the rays will eventually end up in your eye. What we can do is do it the other way around, like we're doing with everything in raymarching. So the camera ray we already have hits the surface. This is our point P, then being refracted, getting eventually to the bottom. But then there's a problem. because from here on, the ray that is that came from the sun, from the light, can be from everywhere. I mean, it doesn't have to be like the reflected ray. Here, what we saw just yet as well. Okay, now with this surface, it's quite okay, but if it's more noisy, for example, you don't know anymore. There are multiple positions where the ray ends up to the bottom. So the only way to really do it perfectly, like physics does, kind of, is going through all the positions, all the rays, and see how much light comes from that direction and add them all up. And this is what ray tracing does, but in a fast way, like finding all the light contribution from every direction and finally end up being like, okay, this is the amount of specular highlight ending up here. But yeah, we are raymarching and we don't have this power. We just want to have immediately result, like, okay, how much light does this ray give us? And that's a little bit hacky what we do, but what we do, we do refract the ray here and end up to the surface here. But what we do here is just simple, the same thing, calculating the diffuse as if there was no water. And this is already making it look what you saw, like watery, because of this refraction. It already gives like a little bit of weird positions of where light is, because you look at different directions. But yeah, perfect would be that it also reflects and really calculates every light. But yeah, we cannot do this. So let's do this. Let's go back into the code. Now, again, very, if you look at this, you might be thinking like, okay, where to start, where to find this direction, what is this angle? Sounds like very higher math, but it turns out we can simply do redirection is refract, also a nice function. So no math involved whatsoever, just put in the incident factor, that's the factor coming from the light, or in our case, sorry, from the eye. And so ray direction, and the second one is the normal. So this factor. And then we have refractive indices. Those are like the value of how fast speed, of how fast light goes through a medium. Like in water, it's 1, or vacuum, it's 1. Air, it is like close to 1, and water would be 1.33, and glass would be 1.52 about. So those values tells us a little bit how fast light is traveling, and we can use those values in the third argument. It should be a ratio between them. So we're going from air into water. And if you're going from water to air, this should be the other way around. So then it's 1.23. Now this just gives us this second green direction. So it's easy as that. We don't even need to calculate any angles. We just use refract and it gives us this direction. Now the next iteration, we updated the ray. So next the next step, the next iteration, we're gonna start from here and ray marching like that, eventually hitting another object. Now let's try it first, see what this does. Lovely arrow again. The normal, I guess it's called N. Yeah. There we go. Now you see like it's way too much bright, too much light, too much energy. And that's because we're just adding. We're adding every iteration and we do 4 bounces. So eventually it adds 4 times the same color. But can we see the refraction if we multiply this with a bit less? Oh no, yeah. So we do change the direction or the origin and direction. But when we start raymarching, yeah, we are already at the surface. So it will return the same distance, 0. So eventually, yeah, we won't move further. So in a way, we need to tell the system here that we're inside the water. Like right now, it just gives the distance as if we were outside the object. But when we are inside, let's do it a little bit hacky, but I like it because else you need to pass it down all the functions. I usually do here some kind of global variable inside. It's not so fast having global variables, but since it's just an integer, it's it doesn't matter that much. Which is inside is by default 0. By default 0, so we're outside. And then after a hit, we're gonna do inside is -1 inside. So we're gonna flip inside. If it's 1, we're inside. If it's 0, we're outside. And depending on if we are inside the object, it's bigger than 0, then it's 1.3 divided by 1.0. Else it's this. Okay, this maybe, I'm not sure you know this, but this is a way of doing a one-line if statement. It's the same as like if inside is bigger than 0, then we do not else. So let's keep it for this to make it more readable. If it's bigger, then we do this. We do that. So the only difference is that we flip the indices. Yeah, now we can use this inside variable inside the scene. Float SDF, signed distance function. And now we can check if inside is bigger than 0. So if we're inside the object, we're gonna negate the distance. So the outside that was positive becomes negative, and the inside that was negative becomes positive. Just times -1. Now, if you look at this now, okay, some side effects, we'll look at this in a bit. But if you look at this now, something is not correct. It's like reflecting. So I made a mistake with the refraction, I think. Ray direction, normal. Think, because the ray direction is from the eye towards the normal, and that one is being refracted. So I would guess it would be like that. The problem is also we end up at P, but P is exactly at the border, and then it returns right away again. So we need to add a little bit. Need to add a little bit to the origin into the direction we're going to, or even better, change the march function here. We start at depth 0, but now we start at depth 0.01. So we're starting a little bit further than on the surface itself, else it will return immediately because the distance to the object is smaller than 0. Now, as you can see, we can look through it a little bit, and weird stuff is happening. But you can see already there is some refraction going on. And the problem is again, like it's way too bright because we're just adding and adding. So the more refractive you get, the more light occurs, and that's not really realistic. It's not like the water gives light. So yeah, then we get to the next step, and that is Fresnel. Fresnel, not sure how you pronounce it. Back to our, oh no, I didn't make any example thing for it, but I can show you here a little bit. Like, yeah, this one. Like with reflective material like water or like glass, a ray is reflecting from the surface back to the environment, but it also depends on if you look next to it, like close to the surface on the right side of a sphere, for example, it gets reflected way more than when you look straight onto it. Like if you look on top of water, you can look through it like a lot. But if you look on the side of the water, you see it reflecting way more. This is called the Fresnel term. And there is a way to model this as well. And I need to have a browser for that. Let's see. That's called, there's something called a Schlick approximation of Fresnel. This guy. And it just describes like, okay, what is this? What it gives is like the probability of reflection. So the higher probable it's reflected, the less it's probable that it's being refracted. So you get more reflection when this value is higher than when it's not. And what here, it sounds a little bit, it looks maybe a bit confusing, but what this says, R0 is just this, N1 and N2 are those refractive indexes we're talking about, N1 being air, being 1, N2 being 1.33 water. So we calculate this, just subtracting, dividing, and squaring it. And then we can do that. And this alpha, cos alpha, saying here, it's just the same. It's a dot product between the view direction and the normal. It's a little bit the same as the specular reflection we already did. So let's implement this. Let's make a function called Schlick. And what we need is we have our viewing ray, our normal, oh yeah, indeed. There's not much time, so maybe it's better not to do this like real time. We'll just copy paste the equation from here. It's here. So to compare it with what we had, refraction index is 1n. That's the air thing, the water. So here this R is R0. We square it, and here we do the angle between the normal and the ray direction and power to the 5. We get a value. If you now use this, Schlick ray normal 1.23, for example. So do this beforehand. So if it's reflecting, we're gonna multiply it with the probability of reflection. So if it's reflecting 100%, this would be the only color, and the rest, let's make some kind of energy component starting with 100% energy. We multiply with the inverse of the probability. So all the rest is being transferred into the next iteration. Now this energy is quite nice, so we can use this to multiply with the color. Oh yeah, indeed, Rui, thanks. So we can multiply this with the color, and then we get code. Yeah, then we get this. So as you can see, if you don't do the Fresnel is always 1, then it gets fully reflected. If it's 0, then you don't see anything. But now, yeah, now if you look at it, you're going through it. But if you look at the surface, it's getting more reflected. I'm afraid I cannot like doing everything live because we only have 10 minutes. So might be better just to now get the demo file and walk through that. So here, this is where we were, but in a different way. Here, so we calculate this slick. If it's inside, we should flip again the refractive indices. Then we're going to multiply it and leave the energy with the rest. And the next iteration, the energy became less. Here, if we hit the background, we added some gray color, and now it looks like this. Oh, I forgot the deformation. Oh no, we did this with the noise. So what I did here is a deformation of the tube radius is a sine wave. If you look at this, tube is tube. Yeah. So this water stream radius will be this. So depending on the y and some time, t is time, time, we're gonna do a changing the radius of the stream, and because we move it downwards, we're adding time. If you minus time, it goes upwards. You get the feeling of like stuff going down. Yeah, this is about, okay, now I colored it as well. Oh, and one more thing I did here is besides like this multiplying, well, no, I didn't do it here yet. But what a nice trick is that if you go through water, that some of the energy is lost, but not like every energy, but only a certain color. So a little bit of the color, and then you get into this one, where the water is less translucent. Yeah, here. Some exponential decay, depending on how far we travel through the medium, we can decrease the water a bit. And then you get like a colorish water thing. You can even make it darker. Almost not transparent, but still it's transparent. This gives like a nice effect, I think. Can really color the water. Okay, one other thing that makes it look better is using environment color. So what I did here is adding an equirectangular map, a map, a 360 map. and then using a nice function called TDCubeMap to equirectangular that can input like a direction, a normalized vector again, a reflective direction or something, and it gives an UV coordinate of an equirectangular map. So then we can use texture to sample from that map and sample the environment color, and use that to also add to the, instead of diffuse lighting, because water doesn't have diffuse lighting, we're gonna use the environment light to reflect it. They get more like reflection of more interesting behavior of the light. And let me see, 10 more minutes. Oh yeah. One part I also think is nice to explain. Here I did some more deformations. So besides the sine wave I did in the stream, I also added some TD simplex noise only on the bottom, so you get like a more realistic feeling of water. Well, realistic is a big word because it doesn't really look realistic, but you get the idea. And I deformed also the bottom. Okay, in this case a box, not a tube, but the bottom tube. And I did this in a different way, not with just functions, not just code, but by sampling a height map. So what I did is like create a top function as a height map, and then instead of in the scene, instead of deforming the height by some kind of sine function, we sample from the UV depending on where you are at the moment, finding the UV coordinates, scaling it depending on the size of the box, and sampling the height map and use that as a height. So now we can control the height with tops. Might be easier to work with noise. You see, again, those are not real distances. So you get like crazy problems of the raymarching because, yeah, it jumps inside the water and stuff like this. So you have to be careful with doing it in this way. But yeah, small distortions and stuff is definitely possible. Okay, that's about the deformation. Yeah, and one more thing, that is adding multiple objects. We saw already you could take the min of two objects, two distance functions, but you also would like to have like different materials. Like one should be translucent, but the other one not, like this box. So, and how to do that is instead of the scene function returning the distance, it returns now a fact2. And a fact2 being like the distance and some kind of ID, some number, some integer telling which object we are. So here, this is the water stream with the deformation of the noise here. And then finally, object X is then the smooth min of those two. And an object Y here is an index, one being water. And then later on, here I built the box. And then you see here, the distance to the box is this guy. And then I use a function opunion. And it's just a helper function that does an if loop. If the distance of A is smaller than B, then return A, else B. So we can do this is kind of the alternative for the min function, but having also an ID with it. Now, when this ID is being returned by the scene, eventually being returned by the march loop instead of a float. It's also a fact2. And then we can simply, after or in the raymarching, after the raymarching, we can simply check if this object is one or not. If it's not, then we're going to break the loop because then we ended up something diffuse. If it is, we're gonna do it again, go further and find the vinyl position. Well, yeah. I think that was it for the main workshop. Sorry for the last part that I went through it super fast, a little bit out of time. Yeah. Oh yeah, one more thing is appendix. If you want to look further, want to learn more about it, definitely check this out. One part is hybrid rendering. If you would like to include raymarching with a normal render top, you can use the depth top, the depth of the camera of the normal renderer, and use that as the maximum distance of raymarching. So when you hit the depth, that would be at the end of it. And if not, you just do your raymarching, and then eventually, I think I do some mix or something. Oh yeah, if the distance is smaller than this, that's weird. Oh no, yeah, here. It's taking taking the depth of the camera. It's either marching until that depth, or when the maximum camera depth is used, is reached, which is here, the far thing of the camera. But anyways, check it out if you want to merge it. It's perfect for like volumetric fog or stuff like this. You have a complex scene and you want to have some kind of light effects. This is super nice. Not so good for refraction because you cannot really sample from different direction of the render top. You only have one view. So yeah. If you want to make more complex materials, geometry, you can do the same thing, kind of what we did with the min. So take a minimum of multiple objects. But yeah, there are more tricks to do so, like cutting things. So we start, for example, with a torus and cutting it in a quarter, and adding another tube a little bit, smooth minning it, doing another tube from the inside and subtracting that. You can add more and more steps, and eventually getting to a shape like this, faucet kind of shape. But yeah, you can imagine with the simple operators and simple geometry, you can get quite complex stuff like this. This is nice. This is just a tube. Adding a sphere, a small sphere in the center of the tube, which you don't see, but using smooth min, then it already gets like a little bit more organic, smooth. Definitely check this out as well. The code is definitely not optimized, and yeah, it's not the best code I ever wrote, but it tells you the idea. Here's the thing itself, which I guess it doesn't work on Mac again, sorry. And yeah, and then the last one, I made a small list of very, what helped me a lot, especially linear algebra. If you're really want to learn about GLSL, linear algebra is definitely something to check out. For the first introduction, the essence of linear algebra, 3 blue, 1 browns, it's the best. If you want to really go in depth, Gilbert Strang is perfect teacher. And this one is also very interesting. Carlos Zolnay here. He's the guy from 2 Minute Papers, and he had a lecture about ray tracing. It's not so much about ray marching, but more about light itself. But yeah, it's really like refraction, reflection, all those stuff is explained very well in this YouTube series. Then all the articles of IQ. Also the videos, very nice. This live coding session really gets you a depth feeling of ray marching. And then the link of the slick approximation we just checked. And that's about it. So thank you. Thank you for listening. I hope you understand a little bit of my mumbling, jumbling. And yeah, it was a bit hectic in the end, but hope you liked it.
Thank you, Tim.
Yes.
Thank you so much for your workshop. Do you have some minutes for Q&A session if you have some time?
Definitely, definitely.
Okay,
Yes.
so yeah, everyone, if you have any question, please post on YouTube comment. Maybe there's some time lag over there, but he could answer if you guys have something.
Thank you, guys.
Thank you. Bye then. Sure. Yeah, I think you did a really clear explanation for difficult difficult concepts. So I think everyone seems to be okay.
Yeah, the only part, yeah, the last part was a bit
Yeah.
fast. Might be that some part is a little bit confusing.
Mhm.
I included most of the shaders also with comments, so it's also.
Oh, Tim, the Lob asking, could this be done with Ray TK?
I'm not sure. I never used Ray 2K from Tect, right? I think he was playing around with it, but I'm not sure he implemented the whole refraction part yet. But eventually, yes, it could be done. And if not, then you can build your custom plugin, I think, for Ray 2K to make it work.
Okay. I'm gonna answer the question from Louis Gato, and we actually we did a recording, and then we're gonna make this available on our Patreon. So if you can join our Patreon, you can watch the recording.
Okay.
That's a run. So question from Jared, can we make coding like this easier if we increase the premium types to start? But after that, can we make shading easier too?
Make coding like this easier if we include primitive types to start. Like the primitive types as the shapes, you mean, of the raymarching, or the things like the ray struct I did here. I don't think there is much you can include in TouchDesigner already to make it more useful, because it's most of the time it's quite unique, and most of the time you want different shapes and different structures. So that's why also rate decay, it's very nice if you don't like programming. Then you can click the same thing together. But for me, it's like, yeah, because of the raymarching, and it's done so many times in your GPU, it's sometimes easier to write code for exactly what you want instead of like finding workarounds and stuff.
So primitive types. Okay.
Yeah, I think Jared means the shapes. Those guys. But yeah, that's some are very hacky. Like, okay, the sphere, that's one. It's perfectly okay in the box as well. But if you look at here, for example, if we take another browser, then you go let's sign distance fields. Yeah, here's the box SDF. Very good. Very good. I have here, of course. This guy. So there are a lot, but like the sphere is exact, but there are also a lot that are not exact, like this one. So it's a very easy way to make a cone, and it works in most of the time. But in some, like refraction, you need an exact one. and then it doesn't work. So and then you need this one, and so there's not really one way of building your distance functions. And eventually, it's mostly a combination of a circle, a square, or at least what I do, torus, and maybe in a line, a capsule. But all other things I'm not really using much. Maybe a hexadecimal. But I wouldn't include this as default ways of implementing them.
Oh, there are
Sorry.
Another question from the eHero. He said, what graphic card are you using?
I'm using a GeForce 2080 Ti, so it runs quite smoothly here. But I can imagine if you don't have this kind of machine, then it gets quite shocky in the end. You can do some tricks to speed it up, like what we did here with one of the raymarches. Is when raymarching, we're taking here a min step. We're jumping. What I did here is I'm jumping not just the distance to the scene, but if that distance is smaller than a certain min step, then use that min step instead of the distance, so that you can have at least like bigger steps. But again, yeah, if you increase it, and here as well, it does runs faster, but it doesn't look so good anymore because you hit a bit the surface and stuff.